So let's look at number 7. It said, consider how much heat is needed to raise the temperature of 10 grams of water, 10 degrees, and how much heat is needed to raise 1,000 grams of water, 10 degrees. Use these considerations to help you explain the kinetic theory of heat and temperature. What I wanted was, what's the difference between heat and temperature? Really, use this information. Well, let's think about what we were working on. Q equals mc delta T. Well, let's consider the 10 grams of water. Okay, 10 grams. The C for water, 1 calorie per gram degrees Celsius. And I want to go up 10 degrees. And you see why the specific heat has 3 units, because the grams will get canceled and the degrees will get canceled, and I'll be just left in calories, the units for heat. Well, 10 times 10, okay, takes 100 calories to heat up 10 grams of water. Now let's look at the other case. 1,000 grams of water, 1 calorie per gram degree Celsius, that same 10 degrees. Well, this is going to take 10,000 calories. So it took a lot more heat, Q is much bigger, to heat up the 1,000 grams than it did the 10 grams. 10,000 versus 100. This is what I wanted you to do. I wanted you to use this to explain the idea behind heat and temperature. What's the difference? It took a lot more heat to heat up 1,000 grams of water than it does 10 grams of water. Because what are we talking about when we say heat? We're talking about the amount of energy in something. A lot more calories, a lot more energy for this 1,000 grams to get it to the same temperature as the small amount. So temperature is a very arbitrary thing. We think about it, we talk about it as if it's the heat. You know, it's 50 degrees. That's how hot it is, or how cold it is, depending on the context. Because in some circumstances, 50 degrees might be pretty cold. After all, if you've been out running around in 90-degree heat, so we even say the words that way, and then you come into an air-conditioned room that was only 50 degrees, it'd be cold. Temperature's a relative thing. Kind of depends on what you were doing before. I one time got on a plane, went up to Oregon, got out, everybody was walking around like in shorts and bathing suit, and it was 60 degrees, and I thought it was freezing. That's because here in town, it had been 100 degrees. That 40-degree difference, it felt very cold. So that was the idea behind this problem, was to see this difference. Now, let's look at 8. Assuming no loss of heat to the environment, what is the final temperature of 10-gram sample of water at 60 degrees mixed with a 15-gram sample of water at 40 degrees? Okay. I'm going to use C for cold. The cold water, I put hot water in it. Okay? It's going to get warmer. Isn't that what happens when I have cold water and I put hot water in it? It's going to warm up. I have hot water. When I mix it with cold water, it's going to cool off. And its final temperature will be cooler than it started. It cooled down because I added cold water to it. So this guy is going to be negative because it cooled down. It got colder. Now, because I say no loss of heat to the environment, the cold water is going to get warmer because the hot water warmed it up. Well, that energy came from the hot water. So, to make this work, I have to add an extra negative sign because positive does not equal a negative. The hot water got colder. It's going to be a negative value, but I have to add an extra negative sign so that these will actually be equal. Because normally a positive number is not equal to a negative, but an extra negative can make a negative and a negative be a positive. So this becomes the mass of the cold water times specific heat. The final temperature of the cold water minus its initial temperature of the cold water has to equal the negative of the mass of the hot water times specific heat, and then the final temperature of the hot water minus its initial temperature of the hot water. And again, this is because we're not letting it go anywhere else. The heat that the hot water lost went into the cold water. Now I can throw out the C's because it's the same 1 calorie per gram degree Celsius for water on both sides. And now also consider, well, gee, hot water, cold water mixed together ends up as warm water. Whatever temperature it is, it's the same final temperature. I can't really tell the difference anymore between hot water and cold water once it's mixed together. It's just warm water. So let's put in our numbers. Well, our cold water, we had 15 grams. And I'm just going to use TF for the final temperature. It was at 40 degrees. And we had 10 grams of hot water, and again it ends up at warm final degrees, but it was at 60 degrees. And that's what I gave you on the board. And some of you wrote down what the right answer is, but how'd you get that right answer? Well, you need to solve. So first off, they both have the grams, so we can just throw that out. We don't have to keep carrying that. Now distribute. 15 times the final temperature minus 15 times 40. That's 600 degrees. And then over here I have minus 10 times the final temperature. And then a negative times a negative. That's also 10 times 60. That's also 600 degrees. Now we need to solve for the TF. Well, I'm going to move that one to the other side so I can combine the TFs, and I'm going to move that to the other side so I end up with 25 TF equals 1200 degrees. Divide both sides by the 25. And there's how I get the 48 degrees. The problem is most of you did not show me that. You did not do that. You did not solve that problem. But that's how you were to do problem 8. Now let's look at problem 9. And again, we can only do these because we're assuming there's no loss of heat to the environment. The hot water's heat went into the cold water. Okay, final temperature is 16 degrees. A 45-gram sample of water was at 10 degrees before mixing. What was the temperature of a 75-gram sample of water before mixing? Hey, the 75-gram sample must have been the hot water. How do I know that? Because the 45-gram sample was at 10, which is less than the final 16. Think about it for a moment. Okay, the final temperature has to be between the other two. One was at 10. The other one must have been more than 16 because the final temperature has to be in between. A mixture. It's warm. Warm is higher than the cold, but less than the hot. Okay, but we're going to have that same kind of starting point. And again, C for hot, or a C for cold, H for hot. We don't need the C's because they're both water. We would need the C's if, say, instead of hot water and cold water, maybe we had a hot piece of metal put into cold water. We could still do this equation, but then we would need the C's because the metal would have a different C than the water. All right, now let's start putting our numbers in. Okay, we had 45 grams. Final temperature was 16 degrees. The cold water was at 10 degrees. The hot water was 75 grams. And again, it was at 16 degrees. But we don't know what its initial temperature was. So note, only one thing's missing. This initial temperature of the hot water. Now, 16 minus 10, that's just 6. And I can, again, throw out the gram part. So basically, I'm going to have 45 times 6 degrees. And over here I have the negative 75 times the 16 degrees. Now the 45 times the 6, that's 270. Okay, let's divide the 270 by the 75. And so basically I have 3.6 degrees is going to be equal to 16 minus, and actually that's a negative because I'm dividing by negative 75. 16, subtract the, so now all I have to do is move that 16 over. So 3.6 plus the 16. Now they both have negative signs, so I can just throw those away. And my initial temperature of the hot water was 19.6 degrees. So that's how I solve for that. And you can see what you put down on your paper. Now the last part, number 10, there are actually two questions there. The first one was, under what conditions would the final result be the average of the two original temperatures? So for example, if, say, one was at 20 degrees and the other one was at 40 degrees, the final temperature would be the average, would be 30. So under what conditions would that be true? And then there's the second question, which is, under what situation would it be 2/3 of the difference? Now, it doesn't give you any temperatures, but to kind of make it simple, we could say, pick something in which 2/3 is easy to do. So for instance, you could start off one at 20 and say make the other one 50. The difference between those is 30. So 2/3 of 30, that's easy to do. 2/3 of 30 would be 20 degrees, which means the end would be at 40, because that's 2/3 of the way from 20 to 50, 20 over 30. So that's the idea. Under what conditions would that be true? Well, let's go back to the first one. Again, we have our M of the cold, the C, and the delta T, TFC minus TIC, equals negative the hot, C, and then TFH minus TIH. But you already got all your temperatures. Okay, so over here, and again, we don't need the C's because they're both water. So the mass of the cold water, well, it went from 20 to 30. And the mass of the hot water, it went from 40 to 30. So notice 30 in both cases. That was the final temperature, the average of the two. Well, over here, I have basically 10 degrees. And over here, I would have a negative 10, but there's another negative sign. So essentially, I also have 10 degrees. Both the 10s cancel out. What has to be true? The mass of the cold water had to be the mass of the hot water. They had to be equal masses. If that's true, I will get an average temperature from the two I started with. And it doesn't matter which two temperatures I start with. This could have been 10 and 20. This could have been 100 and 200. The final answer, the final temperature, will always be halfway if the two masses are the same. Likewise, 2/3, I could do the same thing. I could pick any numbers, and as long as I pick the final temperature to be 2/3 of the way between them, set up the same kind of equation, and you could find out that in fact one of them had to be twice the mass of the other one. The hot water had to be 2 times the size of the cold water, and you will end up with an average that's 2/3 of the way. So that's what I wanted you to see with number 10. In other words, you could, using this equation, actually figure out how much cold and how much hot water you needed to get whatever kind of final temperature in between the two you wanted. Halfway, 2/3 of the way, 3/4 of the way, you could adjust the masses to get that final temperature. So that was the idea for these problems. And of course, we could adjust this and use the C's if instead of 2 samples of water, we say had a really hot piece of metal that we then put into the water, and we wanted to, say, raise the temperature of the water to a certain amount. So that was the idea behind those bottom questions there. Really, over and over again, one equation, Q equals MC delta T. Any questions?